Hey everybody, welcome back to a Robinson rant. And yeah, let's keep going. So I'd like to use this video to discuss a new mathematical concept called Fourier series. Fourier series. And in particular, what we're going to try to do is model a function in terms of a linear combination of cosines, and sines. And I'll try to give you a little bit of an argument for why this can be done, and then we'll go off and look at an example. So the first thing I want you to consider, and this is the basis kind of the entire idea, consider for a moment two functions. We'll call it cosine of 2 pi n divided by t, and then t, cosine of 2 pi m divided by t times t. Okay. And here I mean for n and m to both be integers. So I'll say they are both integers. Okay. And furthermore, let's go ahead and say that n is not equal to m. Okay? Now here's the interesting thing that I would like you to consider. Take a moment and tell me, what is the result of this integration? Go ahead, take a minute. Excuse me, one more point to add. Let's go over a full period. So I have 0 to t. Okay. Go ahead, take a minute. You got it? Good. Yeah, sweet. So you probably notice, and we'll walk through this, you probably notice that because you have two functions being multiplied together, you're probably going to think about product rule or integration by parts. And furthermore, these are infinitely differentiable and integratable. Okay? So we're not going to do integration by parts once, but we're going to do it twice. So let's go ahead. And you're probably familiar as well, repeated integration by parts. I'll go ahead and call this u, and I'll set this one being dv. And so what we can do for repeated integration by parts, so I'll write down u, that's 2 pi n divided by t times t. Differentiate once, so I get a 2 pi n over t sine of 2 pi n little t over big T, and there's a negative sign there, and I'll do it again. Negative 2 pi n over t squared cosine of 2 pi n over t. Okay. And we'll stop there. That'll be sufficient enough for us. Similarly, we'll start off with our dv. And now we need to integrate. Okay, so that means that the t goes on the top and the 2 pi m is now on the bottom. And we'll do it one more time. Sweet. And now we have to remember the sign that is associated with each of them. And so these two, we'll multiply those two, and those will get a negative sign. And these two multiplied together will get a positive sign. And similarly, when we multiply those two, we'll have a positive sign in front of it. So we can write this out. We'll have cosine of 2 pi nt little t cosine of 2 pi mt. oops, excuse me, I forgot the t already, t dt. So we'll go ahead and we'll keep writing. And what we have here is the first term, cosine 2 pi nt times t, times the integral of the second. So that will give me a sine of 2 pi m over t. And there's a little t in there. This is evaluated from 0 to t. And we have that t over 2 pi m. Now the next term, you'll notice we have a double negative sign. And so what we have is a 2 pi n over t times this t over 2 pi m quantity squared. And we have that sine of, sine of 2 pi n over t. We have this cosine of 2 pi m over t times t. And again, that's going to be evaluated from 0 to t. And then lastly, we have this plus 2 pi n over t squared, t over 2 pi m squared. And we have the integral from 0 to t of cosine 2 pi n over t times t, cosine of 2 pi m over t, t. Now you might think, hey, we haven't gotten anywhere. We've done a bunch of math. But notice something. This term, which I will underline, this term is exactly the same as that term with the additional factor in front. So I'm going to move that to the other side. And so we can simplify this. We can write this as 1 minus n squared over m squared times the integral that we were interested in, 0 to t, cosine of 2 pi n over t, cosine of 2 pi m over t. Now let's deal with the right-hand side for a moment. Okay. And we need to evaluate at the lower and upper limits for these last two terms that are still there. Now you'll notice the lower limits, easy peasy, no problem, because each of these terms has a sign in it. And you know that when you evaluate sine of 0, you get, 0. So already the lower limits of integration are taken care of. Sine of 0 is 0. Well, what about the upper limits? At the upper limit, we get something that says sine of 2 pi m over big T times big T. And the big T's cancel out. And then we end up with sine of 2 pi m. And remember, m is an integer. So what can you tell me about the value of this? It's 0. Both of these other two terms, these other two terms give me a value of 0. Okay, so maybe that's not surprising. Maybe that's not impressive to you. Here's the clutch now. Notice this left-hand side of the equation. I have a number times a second number equals 0. Okay? And you have two options there, right? It could be that this first term is 0. And under that condition, that would mean that n has to be equal to m, right? And I said, oh, wait, we're not going to have n is equal to m. Okay, so that option's out. There is no way, under the situation of n not equal to m, this first term can't be 0. What does that mean about the value of the second term? It has to be 0, right? This must be 0 under the condition that m is not equal to n. That implies that the integral from 0 to t of cosine 2 pi m over t cosine of 2 pi n over t, that must be equal to 0. Oh, that's so cool. Yeah, that's really sweet. That's a really cool mathematical thing. Okay. The technical term for this is that we say that the two functions are orthogonal. Okay. When you hear the term orthogonal functions, what it means is that the integral of the two functions is 0. And notice here, it's not by accident that I chose big T to be the limits of integration. Okay. So these two functions are orthogonal over a period of time, big T. Cool, huh? This leads into a whole branch of mathematics, and in particular, if you ever hear the term Hilbert spaces. Hilbert spaces. Okay. What these are, okay, a Hilbert space is a set of orthogonal functions It's a set of orthogonal functions that can be used to represent any other function. And I'll say any other function over the specified interval. Now let's sit back and think about this for a second. Okay. If I have a Hilbert space, okay, I can take any function and represent it as a set of orthogonal functions. And I should go further. Usually it's a linear combination. Okay. So I find a set of orthogonal functions. Any other function in that domain can be represented as a linear combination of those functions. And in fact, we've already dealt with a Hilbert space before. I didn't call it a Hilbert space, but you probably already know it. Yeah. Can you think of a situation in this class where we have represented a function as a linear combination of other functions? Yeah, you got it? Yeah, we've done this. We've represented it as a linear combination of powers of x, right? Don't forget, the polynomials are a function. Okay? And we have seen where we represent a function as a linear combination of other functions. Okay? Our Taylor series. Okay? And you say, well, Greg, what was the domain? What was the specified interval? Here, the specified interval would be something like negative infinity to positive infinity. Pretty cool. So why do I go into this? Okay. The polynomials do indeed create a Hilbert space. Okay. You can use those polynomials to represent functions over the specified interval. And remember, the only restriction on those functions was that they had to be nice. They had to be smooth and continuous, right? In other words, the derivatives have to exist. Okay? Now, this idea of orthogonality of the cosine functions, or even the sine functions, and double check. You should also check to make sure that cosine of 2 pi n over t, 2 pi m over t. Go ahead, check it for yourself for a second, but it's always good to verify that this is also equal to 0. I'll leave that for you, but you should be able to do that one as well. Okay? So what we say is that any function that has periodic boundary conditions, in other words, after some amount of time, the function repeats. Okay? So any function, any repeating function, if your function repeats, if it is periodic, then we can represent it as a linear combination of sines and cosines. I'll put an cosine of, I'll put 2 pi n t over big T. I'll set this one equal. This is a different, they don't necessarily have to be the same number. So I'll put m. Okay. And this is known as, I believe this is known as Fourier's theorem. Fourier's theorem. Any repeating function can be expressed as a linear combination of sines and cosines. Now the trick is, okay, how do we get these unknown coefficients, a and b? Okay? And that's known as I've already hinted at, Fourier's trick. So let's get an idea, and you can see pretty quickly how this is going to work. If you understand the orthogonality of cosines, the orthogonality of sines, then Fourier's trick should hopefully be fairly straightforward. So let's get at that. So Fourier's trick works like this. I've written down my function, which can be expressed as a linear combination of cosines and sines. And notice these summations go from n equals, say, I don't know, n equals 0 to infinity, and m equals 0 to infinity. And now what I'm going to do is I'm going to multiply both left and right sides of the equation. And I'm going to multiply it by a specific value. I'll call it cosine of 2 pi, I guess, p times t over t. Okay? And p is a specific integer. Okay? Now, of course, if I do that to the right side, I need to do that to the left side. So I'll put cosine of 2 pi pt over t. Okay? So nothing funky there, but here comes the magic. Not only can I multiply both left and right sides of the equation, but the other thing I'm going to do is I'm actually going to integrate. And that is the secret sauce right there. We'll integrate from 0 to t, and we're integrating our time. Now, of course, because I'm multiplying, I can pull that in, so I can distribute that. So you can think of this as being from 0 to t of the summation n equals 0 to infinity of an cosine of 2 pi nt over t, and the cosine of 2 pi pt over t dt. Okay. And then, of course, you have that second integral from 0 to t in the sine and the cosine. Okay. Let's focus on this first term for a second, just for sake of space on our page. Okay. Now, you could also, if you want it, you can expand the summation. Right? So let's go ahead and do that. So what you would have is something like 0 to t of a0, right, the first term, cosine of 0, cosine of 2 pi pt over t dt, right? And then you have the plus 0 to t a1 cosine of 2 pi t over t cosine of 2 pi pt over t dt, right? Plus dot, dot, dot. You can keep going, right? Because n is going to go from 0 to infinity. So the next one would be 4 pi t over t. And then, 6, 8, 10, yada, yada, yada. Okay? Now here's the question for you. Ready for it? Let's look at this first term now. If p does not equal 0, what's the value of this first term? 0, right? We've actually already shown that. We showed previously that if p does not equal n, then this integral is 0. And so this is the trick. This is Fourier's trick. By multiplying by cosine 2 pi pt, that will single out only one term in that entire summation. It pulls out the only term where n and p are the same. Okay. Everything else, all the other terms, are 0. And so I can write now 0 to t f of x cosine of 2 pi pt t dt is equal to, all the other terms are 0 except for one term where n is equal to p. Okay. So I usually have an. I will now set it equal to p. It is a set value. Okay. And then I'll have cosine, so I'll have the integral from 0 to t, ap, which is a constant, cosine of 2 pi pt over t dt. And remember, I have 2 of those, so this is actually squared. That's pretty cool, huh? And so now look at this. AP is a constant. I can pull that out. I can pull that outside of the integral. And so at the end of the day, I can write that the coefficient for the pth term is equal to the integral from 0 to t of our function times cosine of 2 pi pt over t dt divided by the integral from 0 to t of cosine squared of 2 pi pt over t dt. Which is pretty cool, right? If I know my function f of x, I can get the if I know my function f of x and I know it's periodic, I can find an expression for the function in terms of sines and cosines. Okay? The coefficients of each term are given by this equation. It actually is cooler than that. Let's go ahead, and I failed to do that previously. Let's go ahead and find what is the integral from 0 to t of cosine squared of 2 pi pt over t dt. You got it? Yeah, good. So usually I always forget these cosines and sine squared things. You could go a couple different ways. I think maybe the easiest is remembering that 1 is equal to cosine squared plus sine squared, and then using our angle summation formula. Cosine of 2 theta is equal to cosine squared minus sine squared. And so if we do something like 1 minus the cosine of 2 theta, we find out, oh no, minus, let's go 1 plus. 1 plus. That way the cosines add, the sines subtract, and I end up with 2 cosine squared. So if I want to integrate this sucker, I can do a trig substitution. 1/2 the integral from 0 to t of 1 plus the cosine of 4 pi pt over t. And that whole quantity is dt. Right? And now you see it, hopefully, right? The integral of cosine over a full period, it's going to be 0, right? So what do I end up with here? I end up with 1/2 t evaluated from 0 to big T. So I get big T over 2. And notice that's independent of P, right? P didn't even play a single role in this sucker. It's a constant, and it doesn't matter what P is. So if I go back up here, I could rewrite this simply as 2 over t integral from 0 to t of f of x cosine of 2 pi pt over big T. There is the equation giving us the coefficients for the cosine term. How about the sine term? Go ahead, hack it out. Yeah, you say, oh, Greg, I've got this. No problem. You end up with B, I'll call it P again, BP is equal to, yeah, you got it, 2t, the integral of f of x sine of 2 pi pt over t dt from 0 to t. Pretty cool, huh? Yeah. So imagine for a minute, and this is a very powerful idea. If I have a signal that repeats, I can express that signal as a linear combination of cosines and sines. And to determine the coefficients for each cosine term, I can use this equation that on the previous page. To determine the coefficients of the sine term, I can use this equation. Same equation, essentially. And therefore, I can replace whatever my complicated function is with this linear combination of cosines and sines. Really powerful. Really awesome. And if you notice some of these videos that I've posted, really nifty too. Like you can all of a sudden draw these really, what would seem to be arbitrary shapes. You can describe them perfectly with some mathematical equations. I'd never seen that, by the way. I knew Fourier analysis, what we're dealing with here, but I didn't realize that you could do that to draw pictures. I mean, like, in terms of adding in the complex plane. Just mind-blowing to me, actually. I was really excited about that. Okay. So I'll let you chew on that. The next video, let's go ahead and put this into practice. Let's take a periodic signal and show how it can be represented in sines in terms of sines and cosines. So hopefully you're looking forward to that. You're excited about it like I am. And yeah, we'll see what happens. Keep up the good work. I'll see you next time.